Hi everyone, welcome back to chapter 10. Specifically, we're still in 10.1 on correlations. Now this is part 2 of 10.1. So previously in 10.1 part 1, we practiced calculating the value for R, the linear correlation coefficient. To calculate R, we practice using Excel's correlation function. We also use formula 10-1 and 10-2. Now in 10.1 part 2, we're going to practice using p-values and also table A6. And remember in 10.1 altogether, we're focusing still on linear correlations. So now let's go into this example. Is there a linear correlation in this set of paired sample data? Previously in 10.1, we worked with data like this. Here in 10.1 part 2, we're going to now work with 23 pairs of sample data. So using these 23 pairs of sample data and an R value that's given to us of 0.801, then using this alpha significance level of 0.05, we're going to answer, is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and the numbers of Nobel laureates? So now this should look a little bit different because we're given an alpha significance level. We're also provided an R value, and ultimately we're going to ask if we do have enough evidence to support a claim for a linear correlation. If we needed to calculate an R value for our set of data, we certainly could using anything we learned in 10.1 part 1. As you may have picked up on in 10.1 part 1, the most straightforward way of finding an R value is definitely using that correlation function in Excel. One thing I want to point out is that this sample data is listed in your book as well, but instead of a value of 5.5 here, there's a value of 3.3. So if you were to replace this 5.5 with a value of 3.3, we'll get slightly different numbers. In the lecture today for 10.1 part 2, we're going to proceed with using this set of data where this is 5.5 rather than 3.3. So I wanted to mention this in case you're following along in the textbook as well. You'll see a value for 3.3 here, and then all the corresponding numbers we get from this data will be just slightly different than what you might see in the textbook. So in solving problems like this, one of the first things I like to do is assign the variables that we're told in the setup of the problem. So from this, we do know our R value already, or we could calculate it if we needed to. We also know N, the number of pairs of sample data, right, where this is one pair. So overall, we have an N of 23. Remember, that's a really important detail here that we don't look at all of the individual data points to get our N. We look at the number of pairs of sample data to get our value for N. The last piece of information we're provided here is the alpha significance level. So we're told that we should use is 0.05. And again, here's this number that slightly differs from the table in your textbook, but we will proceed with 5.5 here rather than 3.3. I also provided you this data in your student outline, so I highly recommend copying and pasting that into Excel either during this lecture or after this lecture and practicing along with me. So we'll go through all of this together, but do make sure you're comfortable doing all of this on your own as well. So in solving this problem, the first thing we need to do is check those requirements that were listed in 10.1 part 1. So for requirement number 1, the first requirement of that our data is a simple random sample of quantitative data. Well, this requirement is somewhat questionable. We certainly do have quantitative data, but when we look at that original data set in the data table on the last slide, it's not super apparent that they are randomly selected pairs of data. So going back here to our original data set, each of these rows corresponds to a country, and we can't really tell if those countries were randomly selected. If they were not randomly selected, then there could be some bias in these numbers. So again, for requirement number 1, it does not appear that the data are truly randomly selected pairs. Here's some additional context of that data set. So we're looking at data between the chocolate consumption per capita versus the Nobel laureates per 10 million people in each country. So it's possible that out of the countries selected for that data set, that they truly aren't randomly selected. For example, to get this data set, we may be in fact just selecting countries that are the most populated. So again, we can't say with certainty that we have a simple random sample of data. So in cases like these, when we can't tell if we have a simple random sample, then we need to keep this in mind once we get our results. So we'll still go through and solve the problem, but the results obtained may not be valid because we have not checked off this requirement number 1, that we do in fact have a simple random sample of data. Let's go on to the next requirement now. So the second requirement of a scatter plot showing a straight line pattern, is that satisfied? Well, let's take a look at the scatter plot. So here's an image of the scatter plot that's provided in your textbook. Here on the x-axis, we have chocolate consumption. Here on the y-axis, we have Nobel laureate rates. Now for requirement number 2, we need a scatter plot to look at. So if this was not provided for us, we would need to make a scatter plot first using Excel. Once we have a scatter plot, we can ask, does this indeed show a straight line pattern? Well, here it may not be as apparent as the straight line patterns we saw in 10.1 part 1, but we can make out a straight line pattern when we sort of draw an arrow in this way. We can also exclude that there's a nonlinear relationship here because we don't see some sort of logarithmic or sigmoidal curve to our data. The only pattern that's most apparent is sort of this straight line pattern. It doesn't visually appear to be a strongly correlated straight line pattern, but we can say that yes, this requirement number 2 is satisfied. Then in 10.1 part 1, I mentioned this idea of outliers, and it's sometimes being tricky to tell if we do have outliers in our data. Again, for requirement number 3, we need a scatter plot, and I'll remind you how we make that in Excel. By visual inspection, can we identify any outliers with certainty? Well, here it's a little bit difficult to tell, but we say that no, we don't really identify any outliers. What about this point, maybe? Could that be an outlier? Well, it's somewhat difficult to tell, but we can almost draw a straight line pattern this way, where this would not be an outlier. We also see that it's sort of reflected on this side of the data, where we could also draw a straight line pattern in this way. So for requirement number 3, what it comes down to is there being an obvious outlier in our set of data. And from this set of data, we can't say that there really is an obvious outlier. So what it comes down to for requirement number 3 is if we can identify an obvious outlier. And here for this data set, we can't really identify an obvious outlier. So at this point, requirement number 1 is somewhat questionable, but requirement number 2 and 3, we can check off as being satisfied. As you've copied and pasted that data from your student outline into Excel, and you're going to practice making a scatter plot, remember we have the data in Excel, then we highlight the data we want, we go to Insert, Scatter Plot, then don't forget to add your axes titles and an appropriate chart title. So when I did this in Excel, I got a scatter plot that looks like this. I remembered to label my x-axis and my y-axis and give this an appropriate title. For a reminder on how to add a title and these axes labels, make sure to go back to one of your past Excel assignments. So we'll keep in mind that requirement number 1 wasn't truly satisfied. So when we get our final answer from this example, we'll have to come back to that fact and consider that. In the meantime, let's continue solving this problem. So in 10.1, I mentioned that we'd use p-values again. So in this part of the solution, we'll use a p-value. When we're using a p-value and an alpha significance value, this should sound familiar to what we did from chapter 8. Here, though, the claims are a little bit different. So if our p-value is less than or equal to our alpha value, then this supports the claim of a linear correlation. Alternatively, if the p-value is greater than our alpha value, this does not support the claim of a linear correlation. So when going this route for the solution, we need our p-value, we also need an alpha value, and we remember that we were given an alpha value in the setup of the problem. So now let's talk about how we're going to solve for this p-value so that we can compare our p-value to our alpha value to then make a conclusion. So to calculate this p-value, we're going to use the idea of a t-distribution with n-2 degrees of freedom. So in order to calculate a p-value, we need a test statistic that we call t. The formula for calculating our test statistic t is here. You'll notice that to calculate this t-value, we need our r linear correlation coefficient. We also need n-2, which is our degrees of freedom. Again, in the problem setup, we were given r, but we could calculate that if we needed to. So let's assign some variables here to solve for our test statistic t, then we can solve for our p-value, then we make that comparison to our original alpha significance level. So we know our n, the number of sample pairs, is 23. Then for our r value, I mentioned there was a slightly different number in the table in the textbook and then the table I have here in the slides. So in noticing this, I went ahead and calculated my r value just to check and see how much difference there would be. So to clarify here, when you have a value of 3.3 instead of 5.5 as it's listed here, you will get an r value of 0.801. So for our set of data here, we're using 5.5 rather than 3.3. So let's go ahead and recalculate our r value and see what that is. We remember from 10.1 part 1, the most straightforward way to calculate that r value is to use the correlation function in Excel. When I use that correlation function in Excel, I get a slightly different r value than if I had used 3.3 in the table instead of 5.5. Let me show you that setup again. So here's all of my chocolate data. Here's all of my Nobel data. I use that correlation function and I get an r value of 0.799517. Notice again that I have 5.5 here rather than 3.3. That's why I get a slightly different value for r. So rather than using an r of 0.801, I'm going to use this value for r for this set of data where I have 5.5 here rather than 3.3. Ultimately, it will make a difference in how we set up this problem. If you want to use 3.3 here instead and use that original r value, that's also totally fine. Now for this formula for calculating the test statistic t, we have everything we need. We have our r value and we have our n value. Then to solve for t in Excel, again, I have my correlation function, that's my r value. I have n, my number of sample data pairs being 23. Then to simplify this just a little bit, I also already calculated my degrees of freedom by taking n-2. Then I set up this formula in Excel, as you see here in this cell. Again, I want to use as many unrounded numbers as possible, so I'm using this full version for my r value, and I'm alluding to that cell here to solve for t. So I type in equals sign, then I click on the cell that contains my r value. That's divided by the square root of 1 minus r squared. Remember how we set up this squared. Then 1 minus r squared is divided by my degrees of freedom. So here's this cell with the number 21 in it. You could have also used a value for n here, but you'd have to do n minus 2 within this equation here. When I click enter, this will give me my value for t, my test statistic. So it's this number here that I get. Again, I want to use this unrounded version of my t-test statistic, then to calculate anything that comes after that, which will now be calculating for our p-value. So to summarize so far, we checked those requirements. We also assigned our value for n. We also recalculated r to see what we get using the correlation function in Excel. Once we know n and once we know r, we can solve for t, our test statistic. So next, now that we have our t-test statistic, we need to solve for our p-value. If you need any refresher on p-values, definitely go back to chapter 8 where we talked a lot about those. So now that we have our t-value, we're going to use this function in Excel to find our p-value. If you're wondering why we're now using a t-distribution function specifically, well, it comes back to this point here. We're calculating the p-value using a t-distribution with n-2 degrees of freedom. Then in this function, you'll also notice this period 2t. This stands for a two-tailed test. Technically, when we're finding this p-value, we really are using a two-tailed test. Why are we using a two-tailed test? Well, that will become more clear towards the end of 10.1. At the end of 10.1, we'll use a formal hypothesis test, including developing a null and alternative hypothesis. What you'll notice when we get there for our alternative hypothesis is that it contains an unequal sign, which we then know indicates that we're working with a two-tailed test. Now, we'll get there a little bit later. At this point, we're still solving for our p-value now that we know our t-test statistic. So in Excel, to use this function of a t-distribution as a two-tailed test, I've started to type this in here where all we need is our x value, where our x value is our t value. So we need x, which we know is t, then we need our degrees of freedom, which is n-2. So again here, because we have our t-test statistic and we want our p-value, in Excel, we type in equal sign t.dist.2t. Then in parentheses, we need our t value for our x value, and we need degrees of freedom, which is our sample number of pairs minus 2. When I click enter to get our p-value, I get a very small number, so 4.7169 times 10 to the negative 6. If you see this type of number in Excel, remember that you're dealing with scientific notation, so really we'd read this as this number. Here's the scientific notation form of the number. Here's the non-scientific notation form. You can see it's a very small p-value. As a reminder for scientific notation, this number in scientific notation, we'd move the decimal point over 6 times towards the right, meaning we have 4.7 times 10 to the negative 6. So we have our p-value. We know it's very small. It's even less than 0.0001. Let's continue on now. We know our p-value. It's very small. We also know our alpha significance level, that's 0.05. So then comparing these two, the p-value is definitely less than or equal to alpha. Based on this comparison, our p-value is less than or equal to alpha. This means this supports the claim of a linear correlation. In other words, we conclude that there is sufficient evidence to support the conclusion that for countries, there is a linear correlation between chocolate consumption and numbers of Nobel laureates. We're going to solve this one other way next, but we'll still keep in mind that requirement number 1 wasn't quite truly satisfied. So this method involves solving for a t-test statistic, then from there finding a p-value. Then we compare our p-value to our alpha value in order to make some sort of conclusion. The other way we're going to solve this now is using table A6 to interpret our R value. So for this method, we'll use table A6, then we'll get a positive and negative value of our critical value, then we'll compare that to our R value. We'll also draw a visual of this to help better clarify what conclusions we can make. So again, we're using table A6 to find a critical value, then we're using the positive and negative form of that critical value and comparing that range to our R value. So what this looks like is we find our critical value, we have the negative form and the positive form. In the middle, we have 0, so we have an equidistant between our negative value and our positive value. In this range from our negative form of the critical value to our positive form of the critical value, we have no correlation. Then outside this range from -1 to the negative form of the critical value, we have correlation. Then similarly from the positive form of the critical value up to +1, this range here means we have correlation. So we need to find our critical value, then we should draw a figure like this, then we plot our R value, then we see what conclusion we can make. So in table A6 in your book, I've cut out some of this space here with numbers we don't need. So when you look at the version of table A6, you'll see a lot more values here between n and 20. For our example here, n is equal to 23, so we know we're somewhere between n equal to 20 and n equal to 25. What we also need when looking at table A6 is the alpha significance value. For our case, again, that's equal to 0.05. That will usually be given to you in the problem, so be sure you're looking at the right column here in table A6. Another thing you'll notice, if you don't see our exact value for n, then we sort of estimate between the available values. In our case then, we know our critical value will be between 0.444 and 0.396. Because our n is 23, it'll probably be slightly closer to 0.396, but we know it's somewhere in between. Now, as you know, I've been a big proponent of using Excel. Here, however, it's almost easier to use table A6 to find your critical value. Now, this is essentially the only instance where I do think using table A6 is easier than using Excel. And again here, we've used table A6 to interpret our value for R to decide whether we have a linear correlation or we don't. Well, what if I do want to use Excel? Well, good news, there is an option. To find a critical value using Excel, we get 0.413. To find the critical value using Excel versus using table A6 is a pretty complicated formula. So in Excel, we need n, our sample size. We also need alpha, our significance level. Remember I mentioned we're working with a two-tailed test, so we put these numbers in here, and then we get an answer for our critical value for a two-tailed test. This is the formula we need to get a critical value using Excel rather than using table A6. All we need for this is our n and our alpha. When I click enter, then I get a critical value of 0.4132. Now, if you'd like to use Excel to get your critical value, I will make this spreadsheet available to you so you can plug in any n and any alpha. I will post this spreadsheet template in Canvas in case you would like to use Excel to get your critical value. In that way, you won't need to type all this in. Instead, you can use this template for your exam and for your final and for your homework. Let's come back here for a second in case you don't want to use Excel, but you want to use table A6 to find your critical value. Then you may wonder, if n is equal to 23, do I use 0.396 or do I use 0.444? Well, 23 is about halfway between 20 and 25, so technically you could take the mean of 3.96 and 0.444. Even better, you could take a weighted average, knowing that 23 is slightly closer to 25 than it is to 20. If you want to talk about how to use a weighted average to do this, please let me know. Another option to be safe is you can plot this range of critical values, then compare your R value to that range rather than to one single R value. Because we do have technology available to us here, we're going to proceed with a critical value of 0.413. Now that we have that critical value, we can make our drawing. So again, we're using a critical value of 0.413. As mentioned previously, we want to use the negative form of our critical value and the positive form. We also want to draw a line, label 0, also label -1 and +1, then add in the negative form of our critical value and the positive form of our critical value. So what this should look like, we have 0 here, then we have our negative form of our critical value, or -0.413. We also then have the positive form of our critical value, or positive 0.413. Between the negative form of our critical value and the positive form of our critical value, in this range, we have no correlation. Then again, between -1 and our negative form of our critical value, we have correlation. There's correlation as well between the positive form of our critical value and +1. Then the R value we calculated can be rounded to 0.800, so we plot that here in the figure. After we've done this, we can now directly compare our R value to the range of our critical values. Now, I've mentioned there are these areas of correlation and no correlation. Now let me show you another way of thinking about it. So we went over absolute values in 10.1 part 1. We're going to use that idea here. For a correlation, if the absolute value of R is greater than or equal to our critical value, we conclude that there is sufficient evidence to support the claim of a linear correlation. In other words, from the figure we looked at, we have correlation if our linear correlation coefficient R lies in the left or the right tail region beyond the critical value for that tail. Again, it's easier to look at a picture like this. So here's correlation on this tail. Then we also have correlation in this tail. Then alternatively, if the absolute value of R is less than our critical value, we conclude that there is not sufficient evidence to support the claim of a linear correlation. Also using the figure, we have no correlation if our linear correlation coefficient R lies between those two critical values. Again, probably easier to look at this picture here. So this is what's meant by the no correlation region. We can see for our example that our R linear correlation coefficient does fall in this region, indicating correlation. Or in other words, our R linear correlation coefficient of 0.800, the absolute value of 0.800, is indeed greater than or equal to our critical value of 0.413. Using absolute values here, keep in mind if we had a negative linear correlation coefficient for R, taking the absolute value of that would make that a non-negative number. For example, if our R, our linear correlation coefficient, was -0.213, the absolute value of -0.213 is positive 0.213. So again, to sum this up, because our figure shows that our R value of 0.800 lies beyond the upper critical value, we conclude there is sufficient evidence to support the claim of a linear correlation. More specifically, we keep in mind what sample pair data we're working with, so there is a linear correlation between chocolate consumption and number of Nobel laureates. So again, we solved this two different ways, using a test statistic T and finding a p-value, or using table A6 to find a critical value. In both ways, we get the same conclusion. Now, though, we need to go back to the interpretation and keep in mind those requirements that we talked about at the beginning. Now, the interpretation here is a little bit funny because although we have found a correlation, it would be, quote, absurd to think that eating more chocolate would actually help win a Nobel Prize. So what we're getting at here is although we can prove a linear correlation between chocolate consumed and Nobel laureates, we need to think critically still. Can we truly connect these two pieces of data, and should we? We'll talk a little bit more about this idea of causation versus correlation in a few slides. That discussion will be interpreting R with causation. Don't go there. Now, if we really think about it, we might be able to connect why a country that consumes more chocolate does indeed produce more Nobel laureates, such as maybe these countries are more populated or they are in a better financial place. However, regardless, we need to be careful about connecting correlation with true causation. I also mentioned we come back to that first requirement of a simple random sample, and because that's not satisfied, the conclusion we make of a linear correlation is also questionable. So what we're learning here is although we may prove a linear correlation, we need to actually think critically about what two pieces of data we're trying to connect. It's also important to note, did we truly satisfy all three of those requirements at the beginning? If not, we need to be cautious as well in our conclusion. Now, one other concept to be aware of is this R-squared value. What this R-squared value gets at is the proportion of variation in our Y data. But to find this still ties back to the linear relationship between our X and Y data. I showed you in 10.1 part 1 how to add that R-squared value to your scatter plot. So you can add an R-squared value that way. You can also use the correlation function in Excel to first find your R value, and then you simply square it. When you square it, you get your R-squared value, so that's another concept to be aware of. Let's practice that calculation now with this example. So from that 23 pairs of data we were working with, we found an R value of 0.800. If you're asked a question like this, what proportion of the variation in numbers of Nobel laureates can be explained by the variation in the consumption of chocolate? Remember, chocolate is our X data and Nobel laureates are our Y data. Then this wording here of the proportion of the variation, that should indicate to you that we need to calculate an R-squared value. So in solving this, we have our R value of 0.800. To get our R-squared value, what we need to do is square this value. One very important thing to note here as well is you should use your unrounded version of your R value and square that. When we square the unrounded version of our R value, we get an R-squared value of 0.639. So again, proportion of the variation in our Y data, think getting an R-squared value. Let's talk about the interpretation now. An R-squared value of 0.639, if we make that into a percentage, that's about 64%. From this R-squared value that we made into a percentage of about 64%, we conclude that about 64% of the variation in numbers of our Nobel laureates, our Y data, can be explained by the linear relationship between chocolate consumption and numbers of Nobel laureates. So the variation in the Y data, the variation in the numbers of Nobel laureates, only about 64% can be explained by the linear relationship between chocolate consumption and numbers of Nobel laureates. Then on the other side of that, 100% minus 64%, that's about 36%. So this implies that about 36% of the variation in numbers of Nobel laureates cannot be explained by rates of chocolate consumption. Again, this came back to finding our R-squared value, making that into a percentage, and then thinking about our definition of an R-squared value. This relates to our Y data, and it connects to the linear relationship between our X and Y data. Now, I mentioned we come to this slide, so interpreting R with causation, don't go there. What this is really saying is correlation does not imply causality. If we can prove there is a linear correlation between sets of data, we still need to really think critically about those results. Again, it doesn't really make sense to connect eating chocolate to winning a Nobel Peace Prize. Next, let's talk about some common errors involving correlation, this whole topic of 10.1. Common error number 1 should sound familiar, so this would be assuming that correlation implies causality. So correlation does not lead to causation. We need to be really careful in making these conclusions. Also, we saw that we had a set of data with 23 sample pairs. Common error number 2 would be using data based on averages rather than based on individual sample results. So we don't want to use averages, we don't want to use means, we want to use individual sample data for these correlations. Common error number 3 we've also talked about. This would be ignoring the possibility of a non-linear relationship. Remember, we can always calculate a linear correlation coefficient R even for non-linear relationships. So not only do we calculate R, but we also need to do a visual inspection of the data. Do our data appear to be curved such that there's a non-linear relationship? Or do they appear to be in a straight line pattern? So we need to pay attention to both the R value and the visual appearance of the data. So now I've been mentioning in 10.1, we'd use formal hypothesis tests, so let's talk about that now. I also asked if you could predict what our null and our alternative hypotheses would be if we're trying to prove if we have a correlation or we don't have a correlation. So if conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, we use the following null and alternative hypotheses. We talked about this symbol notation in 10.1 part 1. Remember, we pronounced this as rho, where rho is the linear correlation coefficient for a population of paired data. Remember R for a linear correlation coefficient, that was for sample data. So again, rho represents the linear correlation coefficient of the population. So for our null hypothesis, it's that rho is equal to 0. Therefore, we have no correlation. From this null hypothesis that contains an equal sign, can you then figure out what our alternative hypothesis would be? So the null hypothesis, rho is equal to 0. Then our alternative hypothesis is that rho is equal to anything other than 0. So again, null hypothesis, we have no correlation. Our alternative hypothesis, we have correlation. Now, in this formal hypothesis test, we again need that t-test statistic. To remind you, when we solved this example of is there a linear correlation, we used both a p-value to interpret R as well as table A6. Recall for the p-value, we needed that t-test statistic. Then for table A6, we needed a critical value and comparing that to our alpha. For the p-value method, we also compared our p-value to an alpha value. So we're comfortable calculating this test statistic t. We'll also use this same equation again for this formal hypothesis method. As a reminder here, this formula is that the test statistic t is equal to R, the linear correlation coefficient for our sample, divided by the square root of 1 minus R squared divided by n minus 2, where that's our degrees of freedom. Let's try this example now. So we'll use a hypothesis test and a p-value from a t-test. We'll use the same set of data we've been working with, and again, an alpha significance level of 0.05. For our solution, the first thing we need to do is check all three of those requirements. If we were using a completely new set of data, we would need to check those requirements. Here, however, we have already checked those requirements. But whenever you see a new set of data, do not skip this step. Always check those requirements. Then again, as you remember, a big part of formal hypothesis testing is to set up our null and our alternative hypotheses. Within formal hypothesis testing, we also need to keep in mind what's our original claim. So to claim that there is a linear correlation, which is what we're focused on here in 10.1, that is to claim that the population linear correlation coefficient, rho, is different than 0. Importantly here for this example, we're using the symbol notation of rho because we're interested in our population rather than just our sample. So then we also know from the last slide what our null and our alternative hypotheses are. Again, the null hypothesis, rho is equal to 0, meaning we do not have a correlation. Our alternative hypothesis is that rho is not equal to 0, meaning we have a correlation. Now, when we found the p-value earlier, we used a function in Excel for a two-tailed test. And this matches up with what we're seeing here, right? Because for an alternative hypothesis with that not equal sign, that means that we have a two-tailed test. So let's continue on now. I want to give you a little bit more background on these possible values for rho and for R. Remember, these both describe a linear correlation coefficient, either for a sample or for a population. So in case you're wondering why we say that rho is equal to 0 means we have no correlation, and then rho not equaling to 0 means we have a correlation, let me show you these figures. So here on this scale, you see 0 means we have no correlation at all. Then, as we saw in 10.1 part 1, we can have a correlation coefficient of up to -1 up through +1. For a correlation coefficient equal to -1, it means we have a perfectly negative correlation. On the other end, a correlation coefficient of +1 means we have a perfect positive correlation. Then we have this continuous scale between -1 and 0, then 0 through +1. It's clear from the scale that numbers here close to 0 means we have sort of a weak correlation. Another way to picture this is, again, we have 0 where we have no correlation, then we go to this side where we have a positive correlation, then over here with a negative correlation coefficient, then we have a negative correlation. Then for one more visual here, we can also picture these correlation coefficients like this. So coming back to our null hypothesis where this correlation coefficient is equal to 0, that makes sense that we'd have no correlation. Then for somewhat of a correlation, not saying whether it's strong or weak, it would be any number other than 0. So let's proceed with the solution now. Here we still need to calculate our t-test statistic. It will look exactly like we did earlier for our p-value. Again, we may be given R, or we can calculate that. We also need N, the number of sample data pairs. Then to calculate T, we know that's our R value over the square root of 1 minus R squared divided by our degrees of freedom. Plugging in our numbers now, we should get a t-test statistic of 6.100. So either way of doing this next step is totally fine. Previously, we used a t-test statistic to calculate a p-value using Excel. Now, as you may have imagined, there's also a way to get this p-value using a table in your textbook. That table is table A3. To use table A3, we need n minus 2, our degrees of freedom. We also need our t-test statistic that we just calculated. Let's take a look at the setup of table A3. So in the left-hand column of table A3, we have our degrees of freedom. As you look at this visual of table A3, I've again cut out some of this information here in the middle. So as you look at that, you'll see more numbers here between degrees of freedom and the number 21. But for us, our degrees of freedom is 21. Then our t-test statistic is 6.100. Remembering our definition of a p-value, it's the area in one or two tails that declares whether we have significance or not. So to continue talking about the setup of this table, these values up here are actually our p-values. The values then in the bulk of the table is where we'd locate our t-test statistic. So for our case, we locate our degrees of freedom being 21, or n minus 2. Then within this row here, we try to locate our t-test statistic of 6.100. As you can see, 6.100 is not in the scope of this table. If instead we calculated a t-test statistic of about 2, that would tell us our p-value for an area in two tails is 0.05. However, for 6.100, it does not match up to any of the p-values we see here. Then interpreting this table further, we see a t-value of 1.323 over here, then for a t-value of 2.831. What we can see by that is the t-values are increasing as the p-values are decreasing. That means by interpretation that a t-value of 6.100 will have a p-value that's less than 0.01. So again, from this table, we cannot calculate our exact p-value, but we can interpret that it's definitely less than 0.01. And the area I'm looking at again is this portion here in the table. So let's continue piecing this data together. So we know our degrees of freedom, n minus 2, is 21. From our t-test statistic and our degrees of freedom, we found our p-value to be less than 0.01. What we saw earlier when we calculated that p-value using Excel, we also got a very small number. Depending on how many data points you displayed, it looked to be about equal to 0. Now that we have a p-value and an alpha value, we can again compare those two. The p-value being very small is less than our alpha value of 0.05. Remembering this now, so if the p is low, the null must go. Then connecting this comparison of a p-value and an alpha value to our formal hypothesis testing, we decide to reject the null hypothesis. Why is that again? Well, our p-value is less than alpha, so we reject the null hypothesis. Here for the interpretation, as mentioned, we decided to reject the null hypothesis. So we decided to reject the null hypothesis, being that rho is equal to 0, meaning we reject the fact that we have no correlation. That means that we support the alternative hypothesis that we do have a correlation. Therefore, using this process of formal hypothesis testing for linear correlations, we conclude that for countries, there is sufficient evidence to support the claim of a linear correlation between chocolate consumption and Nobel laureates. So overall in 10.1 part 2, we've gone through using a p-value, a critical value, and now also using a formal hypothesis test. Now, one last quick note, again, because our alternative hypothesis contains this not equal sign, we need to use a two-tailed test. It's important to know, however, we can also have these one-tailed tests. So again, generally in this section, we'll use two-tailed tests, but these one-tailed tests can also occur. We would use a one-tailed test, for example, with a claim of a positive linear correlation or a claim of a negative linear correlation. As a reminder, for a left-tailed test, our alternative hypothesis would have this less than symbol. Then for a one-tailed right-tailed test, our alternative hypothesis would have this greater than symbol. Therefore, the null hypothesis is still that rho is equal to 0. But if we have a claim of a negative correlation, our alternative hypothesis is that rho is less than 0. Then on the other hand, if we have a claim of a positive correlation, our alternative hypothesis is that rho is greater than 0. We are at the end now of 10.1. I hope you're all doing well. Let me know if you have any questions. I will see you next time for 10.2.